or template?
Well, we changed all our templates a little while ago.
So we do have the clicker there if you want to use it. Otherwise, just use
I like the clicker.
And then I'll hold up, 10 minutes, 5 minutes.
Yeah.
So that includes the question time.
Yeah, and I go not too crazy with number of slides, so I tried to. Tarek was good about keeping us in line. So the only thing, and as far as volume, how are we doing this?
Once you start talking,
We'll do it.
we'll get Mark to adjust a little.
So I'll wait till we're ready and quiet.
I'll get off the stage and it'll be your show.
Oh, it's okay. There we go. La la la. Good morning. Okay, there we go. Hey, so I'm going to start off with number one. We can hear me okay? It's not too loud? Okay, there we go. Just sometimes in the back I notice, because I've been one of those people standing at the back, I noticed that it was a little quiet. So big thanks to Tarek, my co-author. We've done a number of papers together, and he's good about trying to keep the papers concise and also not too many slides. So I'm trying to buzz through this without doing too many slides. I also have and I'm going to start with the thanks. Big thanks to the contractors and the other consultants and so on in the crowd that have supported us in this high strain dynamic testing business all over. So that's where I'd like to start. Anyway, so we've got an outline here, and the topic here is we have been running into this situation where we have piles, and for some reason go to install a pipe pile, the piles don't want to stop or something, so the piles will end up with a concrete plug going into them, and it's really, there's some challenges with that, and that was the purpose of that is the purpose of the presentation, and hopefully by the end of this we'll kind of agree on a path forward when we're testing these sorts of things. So we're going to look at a couple examples of the dynamic response of a simulated plugged pipe pile. We're going to look at just briefly talk about some previous experience, and then look at a more recent case history where we got to do something that we wanted to do, and we did this stuff, some signal stacking, and then there's some summary and conclusions. So why would we want to modify a steel pipe pile and install a plug? Well, we're talking primarily in this paper about piles that are used on bridge projects. So this might come up on marine things, but it's not something you'd typically do for buildings. But for bridges, we have this issue about scour. We've got seismic, right? So often the piles have to have some minimum embedment in the ground for the lateral demands or for scour. So there's the kind of the driver for this, although we may see other situations where we're driving pipe piles, they don't want to stop. How do we encourage them to not keep going? So what happens is the piles will get modified by placing a blob, we'll call it a blob of concrete over some length, this concrete plug, and the intent is it's to induce plugging, and by inducing this plugging we theoretically should be able to increase the tow resistance of the pile. This is assuming we're in some sort of a sandy or granular deposit, and either get to a place where we're happy with the penetration resistance or the capacity, the resistance that we can mobilize. And again, last year, Juan Carlos talked a little bit about the challenge we have with pipe piles, especially open-ended pipe piles. They typically core once we get to any kind of reasonable diameter. And it's very difficult to show or fully mobilize a tow resistance with a pipe pile in a high-strain dynamic test. We saw that quite clearly, I think, with George Massey Tunnel with the large diameter piles. Again, we get 18 to 20 meganewtons with a high-strain dynamic test, maybe 24 or more with a static test, right? So we're leaving a little bit on the table with so to speak, with the dynamic test. We're seeing over the last, say 13 years now, we're seeing this practice, the use of these concrete plugs is becoming more and more frequent. So, and having been involved in testing them and then trying to figure out a path forward or get comfortable we've learned a few things here. So insofar as the dynamic response of the pile goes, we have this, we need to know what the impedance of the pile is, and that's pretty straightforward. The impedance is basically the steel area time, or the area of whatever it is that we're testing times the elastic modulus divided by the C is the wave speed. Again, stuff we know, we don't have to get into the details here too much. Typically, the high-strain dynamic testing is completed on piles with constant impedance, something like a closed or open toe pile, fully concreted, or something where we've got a known impedance contrast where we adjust the wall thickness for the purposes of corrosion protection or something like that, right? What did we do there? So the deal is when we introduce a concrete plug or change a wall thickness, we have this significant, or can have a significant impedance contrast. The challenge with the concrete is, well, the challenge with the impedance contrast to start is that we get a reflection in the force and the velocity times impedance signal. So we see this big effect that we're going to look at with the simulation here shortly. And we see it we see it significantly in the force in ZV, and we really see it in this upwave, which is just the F minus ZV divided by 2, the upwave signal. And the deal is the impedance contrast can be really difficult to quantify, given the uncertainty with the plug section. You have properties, so we've got a composite modulus issue. Density of the concrete infill, for example, might vary because there's not a lot of control on that, and so on. We've also got a behavioral thing where we don't know if we've got bond or what the bond is like between the steel and the concrete. We have potential for slippage at the concrete steel interface and so on. So signal matching can be further complicated by the plug's relative location in the pile. So if it's near the toe or up near the top of the pile, that will affect how many reflections how many reflections we'll see of this big impedance contrast before we actually see the toe. And also the length comes into play. So the impedance contrast of a concreted section can be several times that of the steel. So that makes it very difficult to kind of figure out what's going on. So again, example coming here. So we've got kind of 3 base case scenarios here. On the left-hand side, we've got just an open-ended steel pipe pile with the shaft resistance going from 0 to 60 kPa. It's 30 meters long, 610 by 12.7. And we're 30 MPa on the steel area at the toe, so it's going through some soft layer bearing on something harder. And then scenario 2, we've got a simulated plug, which is basically doubling the wall thickness over a 6-meter length, 1.5 meters back from the toe, and look at what would be considered some early blows where we're not fully engaging the toe, so just steel area, and then some later blows where we're starting to develop a soft plug. And then scenario 3 and 4 are the same as 2, except for we've doubled the length of this simulated plug. And so nice, if anybody's seen it, PDA test data, they've probably seen plots of force and ZV versus time. So I got a little simulated where my pile is down on the bottom. The dashed black line marks where the toe is, and we have this, which I don't necessarily like looking at, but so we're going to move to the next figure here. And basically, this is the upwave. It's taking the same data that we had here, the top curve minus the bottom curve divided by 2. That's what we normally do signal matching on. And Paul Main would say, well, this is a nice vanilla, at least I think Paul would use that term. He'd call it a nice vanilla type of case, right? Because of this uniformly increasing resistance. I've got pretty good toe resistance, and I call that a pretty nice little signal. But now, if I go and introduce this simulated plug, so that's the green thing near the pile toe, we can see how it starts to have a big effect on the the pile or on the measured signal. So there's my up wave, it's the green signal, and it's not too bad. You can still quite clearly see where the toe is and so on. And there's not that much, and the toe being the dashed line, the 2L over C, 2 times the length over the wave speed. And by the time I go and double, we'll go back. This was the coring condition, so the early couple blows, just looking at resistance on the pile toe. But if I continue to drive that pile, assuming there's no degradation of shaft resistance with the additional blows, I start to engage more and more toe resistance. So we can see this sort of transition from the early blow to late blow after the 2L over CO, so after about 12 milliseconds. Make sense? Again, so the plug certainly has quite an effect on the signal. Now, what happens if we double the length of the plug? Hopefully we're keeping people awake here. Again, bigger effect here, and by the time so there's the early blow after the plug's been created, later blow after the plug's been created. So pretty severe effect on the blow, right? So now we're going to go and look at our previous experience here. We have, over the years, we've worked on a number of projects locally. Port Mann, I think, first time we did this was Port Mann Highway 1. We ran into it also out in a little project out near Hope. And it was this struggle of, thinking that high strain dynamic testing, sort of a black box kind of thing for a lot of us. And we think, well, we can go and test just about anything. But there's some real challenges with trying to model the plug when we don't really have a good feel for what's going on with the plug. So the deal is the plugs are often added. Sometimes we think about them ahead of time and say, well, we might need them, or we get to a place where the piles, or we're having trouble on a project, the piles aren't stopping, they're going longer than they're supposed to be, so there's potential for cost overrun, schedule, all sorts of stuff. So it's like, hey, let's throw some concrete in there. And then the question is, well, how long should that be? That's the subject of a different paper. But often what happens is we're only testing the piles after the concrete set, so we don't really have a good feel for what the expected behavior would be without the plug. And so when you go and if we take this data, and we have this big effect of that change of impedance, it's difficult to separate the effect of the impedance change from the soil response along the shaft, right? And again, if it was steel and we knew, and so if we actually were driving a pile where we had that additional wall thickness and so on, we could go and say, well, input that into our model and so on, because it's an actual known. But what happens with the concrete plug again is we don't know, right? So if we go now to a recent case history here, we've got a project in the interior here, included the use of concrete plugs. The site had compact to dense granular fills, some coarse grained alluvial deposits, et cetera, and then we get into sand down below. And the deal was piles are 914 by 19.1 mil wall, pretty standard size piles. They're installed by pre-drilling through the cobbles and boulders to some depth, 8 meters, and then advanced by impact driving. Problem is now the piles go down 45, 50 meters. That's deeper than I think the client probably wanted on the job, and they're not reaching their termination criteria, which is pretty standard with open-ended pipe piles, because again, we're not able to, once they get very big, they're coring, right? So the concrete plugs were added, I'm going to use the term, as an afterthought to induce plugging. I think it's a great idea here, right? So the challenge on this particular project, though, once the pile's already in the ground some depth, depending on what equipment's available, that has an effect on how deep we can clean out the pile. So in this particular case, they were only able to install the plugs to about 26 meters below the pile head, right? So as opposed to the example we had where we had the plug 1.5 meters from the toe, this plug is way the heck up in the pile. On redriving the pile with the same hammer, they were at maximum energy, so same kind of thing. They were able to go from 20 blows per 250 to basically a refusal condition. So they're getting to a place where they're happy with the resistance. So the plug is doing what it's supposed to do. So the key thing on this job was unlike most of the other projects where we're only testing the piles with the concrete plugs, we have some of the piles were actually tested before the plugs were added. That's what we want to talk about today. So prior to signal matching, so I have this topic, signal stacking, and a few years ago I did a presentation where looking at doing some signal stacking to look at how quickly, if we're doing a restrike test on piles in Fraser River sand, we can see significant degradation from blow to blow to blow. Signal stacking is really handy when you're wanting to look at the development of, say, a mechanical coupler, again, providing the sampling frequencies high enough because you can see changes in impedance, right? So, or the quality of the signals are consistent. So there's a signal stacking, this signal stacking approach is also used in sonic integrity testing, predominantly in Europe, and where they'll look at cast in place concrete piles. They will test a big group of piles and then basically stack all the signals, and what they're looking for is outliers, and then they're going to focus on the outlier because assuming all the piles are installed in the same way, in the same ground conditions, the signals should all be the same. So here we have some stacked signals from the end of drive, looks very similar to the simulation, other than where the toe is, the valley is a little bit deeper, or a lot deeper than it was with the simulation. But it's a fairly vanilla soil. I can see kind of three soil layers based on the shape of that upwave curve. And then when we look at the bottom, we see that we don't even get to see the shaft response before the plug comes into play. And the plug is pretty substantial what it's doing to the signal. Can barely even tell where the toe is. But the key thing here, what we've seen on other projects with concrete plugs, is after the first couple of blows, we start to see a little bit of debonding. So that first peak in the upway would fall off a little. So now this is taking, so the top curve again, the pile without the plug, and the bottom curve is the pile with the plug. So here's now just comparing the two signals. So before is the blue, and the red is the pile with the plug, blow 14 from before, blow 74 afterwards. But we really see this effect of the plug on the pile response. And it's very significant after the bottom of the plug, so kind of beyond that 0.3 or 3 second mark. And so we went and tried signal matching on the pile with a plug just to see if we could do it, and we could get something, but not very happy with the results. And particularly in this case because the plug was so high. So we then went ahead and said, well, let's go and do what we intended to do. Let's analyze the pile without the plug, do it with two separate methods, and then we take what we know from the pile that had no plug. We take the shaft resistance from that, use it for our basis with the pile with the plug, and the only parameters now we're going to adjust are the actual plug properties inside the pile and the toe resistance, because those should be the only two things that are affected. Again, assuming that the shaft resistance hasn't changed a lot from one test to the other, and that's a big assumption. So this is our signal matching that was done on the pile without the plug. So we've got match on the upwave, not perfect, but it's a pretty decent match. FZV, we've got a displacement versus time, and force versus displacement, energy, and so on. So overall, we end up with 5.2 meganewtons, 2.6 meganewtons on the shaft, 2.6 meganewtons on the toe. And if we take the same, now we take that, the shaft model parameters, and we're not getting into the details of all that, we go and run it through, we vary the plug parameters nominally, and basically it was, took the concrete plug, broke it into a number of sections, and then started playing with the properties of those sections until we were able to match the upwave curve before the toe, basically before 2L/C. But over in the middle, we see our match on the upwave. The green lines indicate where the toe is. With the displacement versus time, not quite I'm going to say it's not as good of a match as we had with this other one. And the force versus displacement, again, not perfect, but it's a fairly, I'm going to say it's a fairly happy match. We managed to go from a 2.6 meganewtons on the toe, get it up to 3.9, so a 1.3 meganewton increase, not huge, 1.3, 1.4, depending on the rounding. So conclusions here are keep the plug length as short as possible and as close to the toe, or at least that's what our findings are now. And we would encourage people to do that where they can, although we also show here that we can do it otherwise. If you can, we should be testing a pile before and after the concrete plug placement, or test an adjacent pile that was installed in a similar manner, with a similar blow count and so on. The plug lengths need to be very accurately measured, so we don't have to guess the length, and also so we can assess if there's partial debonding. Stacking of signals is something that I highly recommend on a lot of jobs, just to get a better insight as to what's going on. It's not that common in the industry. Given that the effect that the concrete plug has on the drivability, or the dynamic response and the drivability, we should consider the plug when we're doing our WEEP analyses. And then finally, to validate all these assumptions, it would be great if we had a project where we would be doing a static load test or a rapid load test to actually prove out what I'm trying to say, or what we're trying to say here. So that's it. Thank you.
Yeah, we do have a few minutes for questions, if anyone has any.
JC.
Thank you, Lee, for the presentation. You show a case here in which the concrete block was quite high, and your analysis showed that there was an increase actually in the resistance of the pipe.
Ultimately,
So I'm just wondering, is that, as you say, and as we saw in the paper that we presented together, that in open empires, the toe resistance is developed close to the toe, right? It's just a system. And now you have a concrete block that is up there, and that is showing you an increase in the resistance. So I'm just wondering if maybe that apparent resistance, increased resistance that you got here, is just inertia, instead of being actually soil resistant, right? Because now you have a big concrete mass, obviously it's going to take more force to move that, right? So just wondering if
it's good question. I don't know, but I think the big thing is the pile was advanced in the restrike test. You notice that was below 74, and I think it was probably 100 or so blows in the test with the plug. So the pile had been advanced, and the blow counts, or the driving resistance was increasing as that was being advanced. So we weren't we didn't look at an early, and to answer your question, it would probably be interesting to go in and look at one of the early blows from the restrike test. It's a question of time, but yeah, that makes tons of sense.
So we have a question over here.
Thank you, David, for the presentation. I have one quick question. It's only curious in my head. When you did the analysis and you get the shaft friction, 2.6 meganewton and 2.6 in total, then you put the concrete block and you get the same 2.6 shaft friction and 2.9 meganewtons. So I'm curious about
3.9.
what happened with the internal, how you get the same shaft friction on the two different conditions. One which is probably affected by the internal friction of the soil, and the other one that you force the plug, so the internal friction probably is not there. So how to get the same shaft friction? Probably I'm missing.
Well, again, and I guess to answer your question, what we were doing here was purposely holding the shaft resistance on the, it's a 1D model on the outside of the pile, and we were adjusting the concrete plug parameters, so over that length, and we did not consider the internal shaft friction below the concrete plug. So that, as I say, there's still a lot more work here, but it's I think the big point is, if we were trying to model that without having a basis to attack it, there's just way too many uncertainties to do high strain dynamic testing. And I guess that's the message, is I don't think it's an appropriate method to be testing, or we need to be careful when we go out and test piles with concrete plugs, test them dynamically, and we should be looking at it for a job where we can do a static test to actually confirm this and understand if these models are correct or if there's more work to do. I mean, it'd be great if we could have a project where we could do some Plaxis modeling as JC did last year, but it's something that needs budget. This is all done for fun, right? So, but it's a very good question, right?
But the last point is how you convince the people to do the concrete block and the integrity of the concrete block during the PDA test, and how that is going to affect the long-term performance of the pipe. Because you have this bonding process during the dynamic, testing that is going to how that block is going to be.
There's a paper in the Canadian Journal of Civil Engineering from, I think, the 1990s, where they actually were looking at plugs and dynamic loading and so on in pipe piles. So and they were getting still fairly high resistances and so on with the bond. So one of the things we're seeing with the signal stacking, if the signals are all, when I look at the beginning of the response there, where are we? That one there on the bottom, we're looking at signals, that's 51 to 96, but at that first peak, the blows were relatively consistent from one to the other, so that tells me whatever debonding was happening had happened by the time we started the test, right? What we've seen on other projects is that peak, we'll see from the first blow, we'll start to see this drop off from blow to blow. So that's telling me that there's something happening again. I think it's debonding, but I don't know for sure again.
No, that's great. Thank you so much.
You're welcome.
Well, thank you very much, David.
Thank you.
As a token of our appreciation, please.
Oh,
Nice.
Oh, thank you.
So we'll now have a 30-minute coffee break, so please be back here for 10 a.m.
Yeah.
Okay, so it's specific to the
Yeah.
So I have a laser Get yours up. It's funny, I had them all open. I had all of the brains open, and then one part was closed.